Welcome to another exciting computer architecture class. Given the relatively poor showing of in-person individuals for the class, I think what we're going to do, unless there is some objection, is move our class to an online form factor until we get out of this so-called yellow alert. And they've locked down an entire dormitory at this point, and they put them all on quarantine. And I'm told there's a substantial number of positive cases coming out of that dorm. And so it might be better to be safe than sorry. And at this point, I'm gonna try and see if we can't move the whole thing online. But that'll start on Monday. Today, I'm going to be here in the classroom, and anyone who wants to come by is certainly welcome to do so. Certainly welcome to do so. Yeah, in our last exciting computer architecture class, we were covering homework number 5. Homework 5 is due today, midnight, and I think we kind of beat that one to death, but I'm still happy to entertain any questions that you may have. Does anybody have any residual questions on homework 5? Only once? Only twice? Okay, I think we're gone on homework 5. Homework 5 is now, here's the bag. Okay, homework 5 is now in the bag. There, see? Literally in the bag. So next up on our list of things to do is homework 6. And I had asked people to read the book a little bit about the principle of locality. Can somebody summarize for me, please, what is the principle of locality? And it can be the Zoom folks or the people here in the classroom. Anybody have any idea? Principle of locality sounds like a principle to me. If I don't know the principle of locality, I shall send you to the principal's office. But we don't have that. So what is the principle of locality? Is there a princess of locality? The principle.
Is it like the tendency of a processor to access the same set of memory locations over a short period of time?
Yeah, that's about right. That's not bad. How about anybody else?
Is it like when deciding what things to keep accessible in memory, it's like the last used thing is the thing to first not be, or is the first thing to kind of disregard and when allocating new memory?
Well, in a way, I guess there's a
it's a way to choose what to kind of get rid of when you need to add new things to memory, like what memory bits to kind of forget about and which things to yeah.
There's my CPU. My CPU has to fetch instructions, it has to store data. So that means it needs to have memory access. Inside of the CPU, or relatively close to the CPU, I have a thing called L1 cache. L1 cache could actually be in the chip where the CPU resides. Also, something larger and perhaps somewhat slower is L3 cache or L2 cache. External to the CPU, but also relatively fast in terms of RAM, fast meaning low density, high expense, high performance, is another kind of cache called L3 cache. And then comes this other thing called the virtual memory address unit, which can also be a part of the same chip, although it didn't used to be. And so this is called the virtual memory address coprocessor. And they call it a coprocessor because it is a computer in and of its own right. And so then what it does is it interfaces through the bus to someplace called SD-RAM. And that is synchronous dynamic RAM. This is the SD-RAM that you go to the store for and you buy in little SIM slots or DIM slots or SO DIM or SDD RAM slots, and you slot it into your laptop, and it gives it more overall memory, and that memory shows up in Windows when you go under the Windows system, and it also shows up on the Mac when you do About with the Apple, and you go underneath the Mac and you do the hardware profile. And it shows up in Windows too. There's a command for that. I don't recall. I think it's sysx or something like this. That'll show how much memory there is. Those memory profile utilities do not show L1, L2, and L3. Typically, they can, but they don't typically show it. They don't even show the virtual memory address code processor. The RAM has a performance which is inversely related to its availability. That is, this SD-RAM is less available, and it has a lower general cost. These things have a higher cost, but are more available, and their performance is higher. And what I'd like to do is I'd like to try to access some memory. And the memory is stored in an array, where the array ranges from 0 to n, where n is quite a large number. And as I access the different elements in the array and do work on each of these elements, because one of the elements might be an instruction, then I have to go through a process whereby I decode the instruction and execute the instruction, and then store the output from my execution. I have to have a little finite state machine that goes something like this. My CPU is a finite state machine. And what it does is it does an instruction fetch. That is, it has to go out to memory. That's this array, right? Memory is just an array. And it fetches the contents of that array, and that's an instruction. So it has to go to the array, get the instruction. Then it has to decode the instruction decode. So now it's sitting there figuring out, oh, I need to do an add, or I need to do a subtract, or I need to do a multiply. And then he does an instruction execute, right? He's doing all of this, and it's taking him time. And then he has, multiplied two numbers. Let's say the instruction fetch says A equals A times B. Okay, so now he has to decode the times, then he has to execute A times B. They're a register, then he has to replace the register, and then somehow it has to be written back into memory, because somewhere in memory you have to store this variable. The variable is in memory. And it's not necessarily an L1, L2, or L3 cache. It's sitting out here in this array somewhere on your SD-RAM. So what you want to do is you want to do a memory access. You got to go out to here, and then you have to do something to take that contents of that computation, and you got to write it back into memory. Right? It's doing all of this. It's doing all this. And it's a multi-step process, and it takes CPU cycles to do it, and it takes time. Well, the VMA coprocessor sees this, and it does a speculative fetch look ahead, and it stuffs the L1, L2, and L3 cache with as much of this array as it can in advance. So when this CPU wants to go to the so-called program counter, which is little more than a counter that can be set when you do a jump to a specific address, it'll stuff the program counter with that address, so it'll jump to this address. If you want to branch when the accumulator is not equal to 0, it can branch to an address in here. That's program counter is just a jam loadable counter that otherwise just plain increments. And this VMA processor sees this program counter wanting to get access to this RAM, and it sits there and it says, oh, I see what he's doing. He's accessing the memory sequentially. The principle of locality says that if you can access the memory sequentially, then the prefetch from the VMA coprocessor will generally improve the throughput of your code. It will make your code run fast as it possibly can. So the principle of locality says access memory sequentially, if at all possible. If at all possible. And so what this means to me, the programmer, is I want to take advantage of this VMA coprocessor and its speculative prefetch of SDRAM into the cache so that when my execution, memory, and write back occur, it comes out to be like a little section. So maybe what happens is I take a chunk of this, which is probably in the gigabytes. It's gigabytes. And then I'm going to take a chunk of this gigabyte memory, and I'm going to store it over here, and that's going to be in the megabytes. And I'll take a chunk of the megabyte memory, I'll store it here, and it's going to be in the kilobytes. And I'll take a chunk of the kilobyte memory, and I'll put it in here, and I'll put it in bytes. And this will be blazingly fast. So L1 can be like extended registers, and they'll run as fast as the CPU clock. They'll be the world's fastest RAM you've ever seen. Nanosecond RAM. And then somewhere out here, this will run in hundreds of nanoseconds. And this will be cheap RAM that you could get at Egghead Software or on Amazon or something. And yes, you can buy L2 and L3 cache chips if your computer will take it, and they'll be expensive and they'll be specialized for that CPU. These won't be in standard DIMM sockets, for example, or standard SIM sockets. So that's a, principle of locality tells me it's really good if I can somehow keep my access sequential in memory. Keep my access sequential in memory. How do you do that? How do I rewrite my code to make sure that I can keep my access sequential in memory? Let's assume I'm going to give you a sample code. So let's do, let's do an eraser thing. So I have limited space here because I'm on video, so I'm going to have to do a little erasing. What I'll do is I'll take out this thing. And I'm going to write a for loop for integer x equals 0 while x is less than the width x plus plus. So I'm going to go across the columns. Let's see, like that. And then I got another for loop for integer y equals 0 while y is less than the height y plus plus. So I'm doing a kind of image processing operation. And then I'm going to take my pixel at x comma y, and I'm going to set it equal to some function that does some operation on a pixel. This is known as homogeneous point processing, by the way. X comma y. Homogeneous because the function, whatever it is it does it on every pixel just the same. And then I end. That's a perfectly legitimate program. Nothing wrong with this. You can code like this all day long, and you know exactly what you're doing. But it doesn't take advantage of the principle of locality because we don't know if we're column major or row major in our access. So we rewrite this code to make sure that we have access to pixels, and I'll say the pixels are in an integer. And you can pack pixels into anything you like. You could have floating point numbers that come from the Hubble Space Telescope, or you can have fixed point pixels that have 24-bit or even 32 bits per pixel. Integers are 32 bits. If you have 32 bits per pixel, you get 8 bits for red, green, and blue, and then another 8 bits for alpha, and the overlay plane. So here's a pixel array, which is equal to new integer of, let's say, you want a big image. So it's 4096, I did say 6, right? 6 by 4096, which is 2 to the 12 times 2 to the 12, which is 2 to the 24, which is 16 megabytes. So I've got 16 megabytes worth of RAM sitting here. For all I know, that fits into cache, but I want the principle of locality to make sure that it goes into cache L1, the smallest of caches, which may only be 64. No, 16 meg, maybe less, maybe less. And so now what I do, since I don't have X and Y, since it's not a two-dimensional array anymore, it's a one-dimensional array, I replace this function, and I replace this for loop. In fact, I can even replace this for loop, and I'll just say for integer I equals 0, while I is less than p dot length, which is whatever this number is, 2 to the 24, I plus plus. And now, if I really want to use X and Y, I could, but I don't have to anymore. If I'm doing homogeneous point processing, I could say P of I is equal to F of P of I. And that should enable me to use the principle of locality relatively easily, because this array can be prefetched and made sure that its input and output are currently co-located in L1 cache. And it can look ahead by as large as the L1 cache is, and it can even strobe a big chunk of that in and out as it goes through and does the processing. So in other words, I've done a whole bunch of optimization just because I rewrote the code this way. But then you say, but Professor Lyon, I really wanted to have X and Y in there. And it doesn't work if I don't have X and Y. And I really like X and Y. And I don't understand why I can't have X and Y. And you've got to let me do X and Y. So I said, okay, not a problem. We'll rewrite the code again. This time, we'll go back to the X and Y thing. For integer X equals 0, while X is less than the width, X plus plus. And we'll have for integer Y equals 0, while Y is less than the height, Y plus plus. And now what we're going to do is we're going to create an auxiliary variable, integer I equals 0. And what we'll say is integer I is equal to Y plus X times width. And now P of I is equal to F of P of I. notice what happens here is because y is being incremented more frequently than x, I will always be going linearly increasing in the address space so that you can do the prefetch for the VMA coprocessor. Also notice I introduced the variable I, which could have essentially local definition, but made it so that I wouldn't have to keep reintroducing the variable here. I don't have to keep reallocating variables. And now I've got the same form factor that allows me to increment through x and y. Interesting to note, multiply and add is a single assembler instruction for many RISC machines that can execute in a single CPU cycle. So there's no extra penalty for doing a multiplication when you go through and try and do the address arithmetic here.
Professor?
Yes, sir.
Could you put the first iteration of what you had up there, like when you had the x and y next to that? I'm just trying to see how it's different from the first thing you had.
Right. So what we had before was p of x and y equals f of p of x and y. Right? This is different because now we don't know if the array is being held in a column major or row major fashion. So incrementing by y could mean we're jumping W spaces in order to get to the next address. And it could violate the principle of locality. So when you see good Java code written that tries to embrace the principle of locality, you see this. You don't see that. Moreover, if you wanted to do three-dimensional image sequence processing, it gets even worse because now you're going to have x, y, and then z, where z represents perhaps the image number. And so if you're going through volumetric data like an MRI, now you're going through serious, large amounts of memory. And a lot of that memory isn't in RAM. A lot of it is sitting on disk. And we even left out the disk, but if you think about it, disk is going to access in milliseconds. Milliseconds. That's disk access time. That's 1 times 10 to the minus 3. But RAM is going to access in nanoseconds. Nanoseconds is equal to 1 times 10 to the minus 9. And the difference between minus 9 and minus 3, it's like 1,000,000 times faster to be in the space of RAM. Even for SSDs, it's slow because you're going out through USB 3 or you're going out through eSATA or something like this. Disks are always 1,000,000 times slower than RAM. So
and for modern languages, the compiler or interpreter won't optimize that for you ever, or does that ever happen?
That's a fair question. Not that I've seen. And so I mean, you'd think it should, right? Any compiler worth its salt should take this and turn it into that. Well, guess what? It doesn't. And you can see that when you benchmark it and you see the difference in execution speed. And how big a difference? 6 times slower, even slower. Because why? Because if this memory access is big enough, in other words, if it's 4096 by 4096 by 4096, because that's how many images you have in your image sequence, now that's 2 to the 12 times 2 to the 12 times 2 to the 12, and through the laws of exponents, we add the exponents, and now 3 times 12 is equal to 36, and 2 to the 36 is a big honking number. That's the technical term. I don't even know what to call 2 to the 36. Does anybody know? I mean, it's got to be like a mouthful. It's a huge number. You probably don't have that much memory. You probably don't even have that much disk space, but maybe you do. I don't know. So it's a problem. Now, when I was doing image sequence processing in the 90s, we were doing 11 megabytes per image at 60 frames per second, uncompressed. We were doing 1920 by 1440 pixel images, uncompressed, 60 frames per second. And I was buying RAM with a credit card from corporate, and it had no credit card limit. So if I had to buy RAM, I could get a truckload of RAM. And we could come in and we could store all the images in RAM, and then we could swap them out and swap them in and put them into our little gigabit per second tape recorders for recording all of this. That's how we did image sequence processing back then. This is before people had HDTV. So we were doing image sequence processing essentially to prove that our HDTV system was better than anybody else's. And you had to do stuff like this if you were going to try and get any kind of throughput out of your algorithms. The principle of locality directly impacts how we write our code. If we know computer architecture reasonably well, then we can write code better than someone who doesn't know it well. And so when you talk about homework 6, the title is software optimization. And so what we're thinking about is we're thinking about ways in which to make our programs a little bit friendlier to the hardware that we're going to have to run on. And by the way, this rewrite to this software is good for C, C++, C#, Java, and perhaps a host of other languages that have a similar syntax. I mean, you could probably do the same thing in Python, but the syntax would look different. And if you're going to use MATLAB for your array processing, I guarantee you the underlying linear algebra software libraries have been optimized to make use of this sort of thing. In fact, MATLAB started as a LinPack software library. LinPack was originally written in Fortran. Fortran had column major instead of row major, whereas C and C++ had row major. And Java, they don't tell you. They just don't tell you. Could be anything. It's not part of the Java language specification. And that's a problem. The Java language specification does not tell us how many dimensions is too many dimensions for an array. I mean, that's a remarkable thing. If I have a 10-dimensioned array, maybe that's okay in C. If I have a 1,000-dimensioned array, people would say, what are you, nuts? In Java, it's okay, as long as you have enough memory. That's kind of a big if. So there's a few different ways in which loops can be optimized for software. This is using the principle of locality to operate more efficiently. Let's take a look at another way to do these things. Suppose and there's a question in here that's specifically about loop fusion, also known as loop distribution. And what I'm showing you here does not change what the code does. It only changes how it does it. We call this refactoring. And this is called, this form of loop fusion is called fusion fission. This is loop, we'll call this loop fission. Loop fission, loop fusion, they're inverses of one another. What we'll do is we'll start with for integer I equals 0 while I is less than n, I plus plus. I don't know how big n is, but I have A of I equals 1, B of I equals 2. Loop fission will break this up into two separate for loops. Why would you do that? Here's loop fission. Now we do fission. Fission means to split. For integer I equals 0, while I is less than n, I plus plus, A of I is equal to 1. For integer I equals 0, while I is less than n, I plus plus, and B of I is equal to 2. It's clear. We took two statements and we broke them up into two separate for loops. Why would we do that? Don't all shout out at once. Any ideas? It's principle of locality again, right? This enables memory coherence. Now the compiler can come in and it can say, oh, look, I can run this on core number 1, and this can be run on core number 2. So now if I'm in a multi-core situation, these two things can be dispatched separately, and they're accessing separate memory. And the two different cores can access the two different areas of memory, because A memory and B memory are in two different areas of RAM. And both can be strobed into cache, but into separate caches that are going to reside with separate cores. In other words, if we benchmark it, this code, which is really easy for you to write for large arrays, should be shown to be slower than that code. And the question of how much slower depends on the size of the arrays and whether you can size the arrays appropriately to take advantage of the cache that's residing in your cores. And no, the compiler, at least not yet, as far as I know, is not smart enough to know how to do this. You have to do it. And it's not that much harder, but it can make things much faster. All because you can take advantage of the principle of locality here, and you can take this thing and put it into a separate core, take advantage of the principle of locality here, and they're completely separate programs independent of one another. Sometimes the principle of locality is called memory coherence. And so what that does is it lets me use the cached data. And it allows me to take advantage of multiple cores. Right? This is multi-core friendly. And I like that. I want those cores busy doing my little whatever. I mean, if your goal, think about it, is to mine for Bitcoin, you might be using more, I don't know, energy, right? More electricity to mine for Bitcoin if it takes longer. But if you can optimize for Bitcoin mining in a multi-core environment, then maybe this is one way to do it. So that's loop fission. The opposite of loop fission is loop fusion. So if you go the other way, that's fusion. And sometimes people call it loop jamming. Loop jamming. And so now we have what? Changed the structure of the code, but we haven't changed what it produces. We didn't change the input and the output. We just changed how it operates. So this whole practice that we're engaged in is called refactoring. And if this resided in a subroutine, I would take that subroutine and I would leave it alone, duplicate the subroutine and say, here's the fast version, and then benchmark one against the other and see which one's really faster, to see whether or not this sort of thing is worth it, especially on a machine where I know how many cores I'm going to have when I target the machine, and I know how big the cache is going to be. I'd like to know if it's worth doing this sort of thing, and if it is, I'll keep doing it. Moreover, it's really good when you refactor code like this to test. You must, every time you refactor, you must test. So that means if you have a known good subroutine and you intend to refactor it, keep the known good subroutine, get a framework in there to test it, and then compare the output of the tests. Because if you find that they give you different results, that's not good. You made a mistake. I know it's going to be stupid for you to make a mistake on something as simple as this, but believe me when I tell you, it gets more complicated. Trust me on this. And once you start refactoring your FFT, and you say, oh, I'm going to make my fast Fourier transform faster, and I'm going to use, they have an algorithm called fastest Fourier transform in the West, right? When you compare against it, you better make sure it gives you the same result as the one you're used to using, because if it doesn't, it'll give you answers that just won't be correct. And that's a problem, because you wonder later, how come things don't look right on the screen? So that's the answer to questions 8 and 9. Sometimes fission doesn't improve your runtime speed. And sometimes fusion doesn't improve your runtime speed. So that's another reason for benchmarking. Once you find out these things aren't worth doing, you'll stop doing it. Maybe the runtime speed improves by a de minimis amount that says it's not worth it. In the CPU hardware, you have something called branch prediction. Branch prediction started in the 60s with mainframes at IBM, and it has made its way into modern desktop computers and, yes, even mobile devices today. I probably have branch prediction in my iPhone. And what it does is it attempts to figure out where you're going to go next and prefetch the memory into the cache so that it can gain access to higher overall throughput. So that branch prediction is all a part of what goes on in the virtual memory address coprocessor. Branch prediction occurs inside of what's known as the pipeline. The pipeline inside of the processor occurs whenever you have a modern superscalar processor. The RISC pipeline can have multiple stages, 4, 5. There are diminishing returns to going beyond 5 stages. I mean, you can do it, but after a while, things don't necessarily get faster, and it consumes more transistors. Let's look at a classic RISC pipeline. And I'm going to allude to what is the Flynn taxonomy, which we now know, single instruction, single data pipeline. So this could happen in a SysD machine. I do an instruction fetch. I do an instruction decode. I do an instruction execute. Right? This is a classic single instruction, single data CPU. I do a memory access, and I do a write back. And these things happen in approximately one CPU cycle. RISC machines like to run in one step of the pipeline per cycle. But if the RISC machine is pipeline, as superscalar RISC machines are, then when this instruction fetch is done and this instruction decode begins, he does another instruction fetch. And then while he's doing a decode, this is doing an instruction decode in the pipeline. He's speculatively swapped to the next instruction. He does an instruction execute. Well, this one is executing. He does an instruction memory access if he needs it. And then he does a write back. And guess what? After this instruction is fetched, we can do another instruction fetch in parallel, all on the same SysD CPU. Instruction decode, execute, memory access, and then a write back. And now it's beginning to look as though we have an assembly line going. One guy does an instruction fetch, hands it off to the next guy, goes out, gets some more memory, and does another instruction fetch. This next guy is doing his decode, and then he hands it off to the next guy who does the execute, and he says, give me the instruction fetch for the next instruction. And so in the assembly line, right, we are able to optimize. Consider Sunday. Sunday is laundry day. What do we do on laundry day? Well, we take the ginormous 11 garbage bags filled with laundry, and we start to create the assembly line. We fill the washing machine. Right? Then, after the washing machine is filled, it goes to the dryer. But while the dryer is drying, we fill the washing machine again. And while the dryer is drying, when it's done, we start with the ironing. But now the other dryer is going, and what happens? We go and we fill the next washing cycle up. And so what we do is we try and do everything in a pipeline. Right? Keep everything busy. Keep the wash going. As soon as the wash is done, move it out into the dryer. As soon as the dryer is done, move it over to the ironing. While the thing is drying and washing, you can proceed with your ironing and your putting away. Right? You made a pipeline. You could certainly say that you could have a multi-core situation for your laundry. How do I do that? I take my matching luggage. I'm a student, so my matching luggage consists of many garbage bags. And I take my many garbage bags and I put them in my station wagon and I drive to the laundromat, the model of multi-core processing. And what does the laundromat have? A lot of washing machines. And what do? I fill them all up at once and concurrently go shopping next door. And then when I'm halfway done with my shopping, I go back and put them all in the dryer at the same time. And then after they're done, I don't iron them. I put them all back in the garbage bags and drive home. And I have clean but wrinkled clothes because I'm not ironing nothing. So as a result, I can have a multi-core process that really accelerates my productivity, even though I'll kind of look schleppy as I walk around in my wrinkled clothes. Just imagine what the throughput is when you're driving with all this laundry into the laundromat. And the beautiful thing about garbage bags is the luggage is always matching. That's my multi-core analogy with laundry. I hope that's not too strained, but I think everybody who has to do laundry gets it. Of course, the better way to do it is to take the 11 garbage bags and show up at your mom's house and say, oh, Mom, I don't have a laundromat. Can you do my laundry for me? And she's going to look at you funny, but she'll probably do it anyway because she loves you, even though that love may not be deserved. So that's there you have it. The principle of locality, all related to laundry, because everybody knows about laundry, I think. Branch predictors are going to go out and try and see what the instruction decode and execute result will be. Jump to subroutine 0200. This gives me an address that gets stuffed into the program counter, right? Branch, if not equal to 0, to 0400, gives me another program counter address. These are all assembler instructions, but at some level, the assembler instructions are looked at by the virtual memory address code processor, and they say, you know, I think we might need some memory near 0200. We might need some memory for 0400. Let's go get 64K worth of bytes and put it into the L3 cache. And then if this branch if not equal executes, we'll have it handy. We'll get it ready just in case it's needed. That's called branch prediction. And you can see these instructions coming as they come in. Somebody decoded it, and the VMA coprocessor says, oh, look at this. Branch if not equal, go to 0400. I better go over there and get some memory, get it ahead of the CPU. Why? Because getting memory out of the RAM takes forever. And doing it ahead of the pipeline will keep the pipeline full. It's so important to keep the pipeline full, because if I do a branch prediction and it's wrong, and the pipeline empties out, then all of this hardware becomes unused. And I have what's called a cache miss. And every time I get a cache miss, every time, I'm going to have to empty this pipeline out and then refill it. And that's going to take many cycles. And it's going to harm my throughput. Imagine, if you will, sort of running into the supermarket next door to the laundromat, and the wash is done. Your dryer is now engaged in stop and wait protocol. It's waiting for your wash, but it is not productive because there's nothing in the dryer and it's not running because you're busy doing something else in the supermarket. So that's like a cache miss. Now your pipeline is empty and you're in stop and wait protocol and throughput has dropped to 0. All because you're waiting for laundry for the dryer. It's so critical to check up on the timing and watch the watch, because you know how long it takes wash to get washed. And when you're thinking, oh, I got 3 minutes to get over there and start to move everything, you better get moving, or else you won't have an optimal minimized time for doing your laundry, which, that might be okay for some people. Not if you're an engineer really focused on getting laundry done in minimal time. Okay, we're going to shut up about laundry now. I cracked myself on laundry. Okay, so let's take a look at the finite state machine inside of the CPU. So this is a classic sequence of things that you need to get done. If you think about it, the finite state machine that the CPU has to go through isn't even all that complicated. I mean, you could build a stopwatch finite state machine that's more complicated than the CPU state machine, especially if you got a lot of features or function points. So this relates to question 12. And we're not going to do this for a superscalar machine. We're going to do this for a simple SysD machine. So we'll start off with a reset. And what we're going to do is an instruction fetch. This printed so small, I've got to use glasses. I didn't used to have to do this, but I do now. And what we're going to do is we're going to loop back and wait until we get our memory. And then what we're going to do is we're going to do an instruction. I'll do another instruction fetch. I'll do an instruction decode. Now I got to wait for that to get done. And then I'm going to do an instruction execute. And I got to wait for that to get done. And this instruction execute in here, well, that's kind of like a branch process, right? I don't know what the instruction is. I've loaded the instruction, but I don't know what it's doing. So maybe instruction execute is different if it's a load instruction. I do the load thing. If it's a store instruction, I do the store thing. If it's a get something at an address instruction or an add instruction, then I do the add thing. It's a simple machine. If it's a branch instruction, then I do the branch thing. In other words, I've got to have a separate instruction for every operation that I intend to perform in this CPU. How many instructions is that? Well, here's where things get complicated. The number of operational codes, or opcodes as we call them, is not limited by anything in particular except for the design of the machine. It's not unusual to have well over 100 instructions, although the original PDP-8 only had 8 instructions. And after the load is done, all of these things have to return back to the top. So what we've done now is we said the instruction decode process is really little more than a giant case statement, which essentially says, I'm going to do a different operation depending upon what I see. It's a big dispatch. So instruction decode, we say we're going to do an instruction execute, but what we really mean is, depending on what we decode it to do, it's going to do these different operations. And that's what makes the finite state machine a little bit more challenging to run. It's ringing at me. Is it time? No. Yeah. So let's look at a different loop optimization, more refactoring. And we could build a finite state machine that does just what we're discussing, right? A finite state machine that executes a small instruction set. And because we're digital design graduates, we all know how to build some finite state machines. So here comes a for loop. suppose I needed to do something like this. Now let's assume for the moment I have a vector coprocessor. And the vector coprocessor will let me work with 5 elements at a time. A 5-stage vector coprocessor is not a very big one, but it's the one that they first came out with when they came out with AltiVec in the PowerPC 604. So it's a for loop just like before. But now I equals I plus 5. I'm assuming n is an even multiple of 5. And if it's not, I'll have to modify my code somewhat. But now what I'll do is I'll take do a vec add of a of I starting at, let's say, well, you know what we'll do is we'll pass a in, and we'll say we're going to be starting at location I. It'll move up 5, and it's going to add 1. Yeah. So what this does is it takes the 5 units that are near A, proceeds to add 1 to them, and this is going to jump through and have it offset by another 5 units. So it'll go 5 units at a time. And this little guy is going to accelerate the processing by doing a vec add. You could see vec adds available in CUDA cores. You can see them vec subtract, vec multiply plus add. In fact, they have the so-called tensor processor, which allows you to do the same sort of thing with an array, a 2-dimensional array. In point of fact, if you have a computer program that's optimized to deal with arrays like MATLAB, and it has something like a toolbox that allows you to make use of a vector coprocessor, it can accelerate this stuff for you, but you're effectively giving it arrays to begin with. And as a result, it can break up the arrays using vector addition in order to be able to do operations more efficiently. So a vector is little more than a homogeneous list of elements. It's an array of primitive data types. So primitive data types would be things like floats, doubles, ints, bytes, shorts, longs. In the world of Java, you could even include chars, although doing operations on chars in vectors may or may not make sense. So what we've done here is a form of loop unrolling. And what vec add is doing is it's doing the following. It's taking a of I and setting it equal to a of I plus 1. Then it's taking a of I plus 1 and perhaps concurrently doing a of I plus 1 plus 1. In other words, it's doing a form of loop unrolling. It's doing another a of I plus 2. It'll keep doing that until it gets to ... a of I plus 4. We'll do it in 4 stages in parallel, all at once, and it'll do all of this with a single invocation. And what you'd like to do is you'd like to make it so that you can stride as many elements as possible. In other words, if the vector addition is 100 elements long, then you'd like to do I equals I plus 100. and go in increments of 100. That'd be great. And so this is called, right through here, loop unrolling. And you can do this yourself if you like. And if you have, heavy duty operations that can be run in parallel, like there's a function invocation that can be dispatched to a separate core, that might help you. That might help your speed. So we're up to question 14 now in the homework. How am I doing on time? Good. Any questions so far on this? So I find the discussion is interesting in some sense, because what's happening here is we're gaining access and insight into what's going on inside of the CPU. What I'll do here is, we've seen in the past how a finite state machine can represent in an abstract way what goes on inside of the CPU. But let's take a look at the vector processing unit's role inside of the execution flow. So we have this dispatch, right? And the dispatcher effectively has to say, I'm doing an instruction decode. I have to decide what to do next. If it's a, a floating point multiply, then I have to go and dispatch to the floating point unit. If it's a simple addition between two integers, some sort of integer operation, I'm going to dispatch to the integer unit. But if I've got this wacky, wild professor doing loop unrolling and calling vector addition and vector multiply and vector divide, then maybe I have to dispatch to a separate piece of hardware called the vector processing unit. That used to be kind of like a bag on the side that you could access. They called systolic. And a systolic array processor was a specialized unit, but it's now all integrated into a chip. It's all in the chip. And what comes out could be 128 bits. I mean, this could be a very wide unit. What comes out of the floating point unit could be 64 bits. What comes out of the integer unit could be 32 bits, all different sizes. And it all goes into cache. That's cache memory. And then the instruction stream comes back and goes into the dispatch unit. And now it becomes clear, right? Because you have a variety of different hardware in the chip, the dispatch unit has to know, based on the instruction decode, which hardware to use. Otherwise, what's the point of adding all this hardware? Now, if I'm a graduate of some Ivy League school and I have to come up with a fancy name, I might call this MMX, for multimedia instructions. Or I might call it SSE, for streaming instruction extensions. Or maybe I would call it Altavec if I'm a Motorola employee or an IBM employee coming up with a Power Series workstation. But those are just marketing terms. It's all the same thing, a vector processing unit, that's all. And MMX, not only was it a marketing term, it was a trademark label. They'd put a sticker on your laptop that said MMX on it. And you were supposed to know what that meant. Okay, I'm kind of ignorant about this stuff. You tell me. Did you guys know when you saw MMX on a sticker that it referred to a vector processing unit? No, nobody knew that. It just said MMX. And what was that about? like we were all supposed to go to Walmart and buy a computer. And it says MMX, and we were like, so? Does it run Word? Does it run Excel? I don't care. MMX, it's dark in the box. I don't know from MMX. If it runs my apps, that's what I know. I got the same problem, you know, with the justification of the $5,500 Tesla card. What do I need it for? I mean, are the people who are buying this teenagers? And if they are they doing scientific visualization at home? Or are they just sort of being the kid on the block with the biggest, fastest, baddest computer? I'm not exactly sure. Maybe they don't know what they're buying and why. But I got a feeling there are people who are buying $5,000 graphics cards without a good reason. Or maybe they have one. What the heck do I know? I know I'm not buying one. At least no time soon. But it's nice that they're able to sell them. I have a theory that $5,000 graphics cards serve a useful social function because it takes money from stupid people and gives it to smart people. But I could be wrong about that. There's probably people who buy them for a good reason, other than like playing Doom or something. Yeah, I mean, if you're a competitive gamer, maybe it gives you an edge. All right, so there's classic matrix algebra. And we, in the world of mathematics, do not discriminate between adding up the elements in row major or column major. But in the world of computer science, it matters. Because if we want memory coherence, if we want to exploit the principle of locality, I have to know, if I'm writing a two-dimensional array, if I'm going row major or column major. If I'm going row major, I go this way. That's row major. And if this is X and that's Y, then I want Y to be on the inside of my for loop. Right? If, on the other hand, I'm a Fortran programmer, guess what? I go column major. Boy, that smells good. I wonder if this stuff is healthy. So there it is. If I'm going to have column major order, then I have to make sure that the X is going to be on the inside of the for loop and not the Y. So I have to know if I'm doing two-dimensional arrays, if I'm going in column major or row major. So in Java, this is question 14. We should always use arrays in row major order. Is that true or false? This is a true or false question, you know. In Java, we should always access arrays in row major order.
False.
That's false, right? Because why? Why is that false? Yes, sir.
Well, we don't know which one they use. Right?
We don't know. The Java language specification is silent in this matter. If we're in Fortran, we go yellow. Other languages, perhaps C, we go green. Java, we don't know. So the safest thing to do is to simulate multi-dimensional arrays and use one-dimensional arrays and do some add and multiply, which you can, by the way, do in a single assembler language instruction, which on a RISC machine is done in just one CPU cycle. Suppose I showed you this array being laid out in one dimension. A11, A12, A13, A21, A22, A23, ... Is that row major or column major order? Is this row major or is it column major?
Row major.
Row major?
It's row major, right? Because if you go this way, it's row major. And so if we could get the address of these elements and print them out, we could determine if our array is row major or column major. Does Java store data by address? In other words, can I look at a memory address for any given piece of data? In C, I can do ampersand. Oh, that's not a good color. Ampersand, right? And I can go and get the address for a data type. And so I can print out the address. Can I do that in Java? You can?
Yeah, if you try printing like an object, for example, wouldn't you print out the memory address?
You will get a reference, which is almost a memory address. So if A of int 100 is printed, what you're going to get is a hexadecimal number with a little hash mark. So in principle, you could try and get the contents based on addresses, but I've never tried that. I don't even know if you can. You might try it. It might work. Not sure. It's not clear. I mean, if you tried to treat the two-dimensional array as a one-dimensional array and then indexed into it, then that might help you determine. But unfortunately, the Java compiler may balk at that one. I don't think the compiler would like it. If you forced, you know, what you can do is you can cast, right? So you can say integer P is an array, and then cast the integer array A, where A is two-dimensional, casting to P. No, the compiler is not going to like that. It doesn't know how to convert two-dimension to one dimension. I mean, if you could do that, then you could sequence through P and you could figure out what the elements are in A, even though A may be a two-dimensional element. I don't think Java is going to let you do that one. Unless you can somehow fool the compiler into doing it. I don't see it happening. Maybe what you could do, though, is you could look at the bytecodes after you statically compile an array. So if you do that and you look at the bytecodes, then maybe you could do it. But it would require bytecode engineering. The compiler wouldn't be involved then because you'd just be doing a hexadecimal dump of the bytecodes. So that's what I've got for you for today. I think we're almost out of time. Are there any questions about what we've got here? This is homework number 6. It's due next week, end of day midnight on Thursday. And we're going to switch to an online form factor at this point because the showing in the classroom has kind of indicated that maybe people would prefer to do distance learning by and large. So if anybody objects to that, let me know in a private email. And other than that, stay safe and thank you for your attentions.
Thank you.
Thank you, Professor.
Thank you. Let's see if we can stop the recording.
Thank you, Professor.
Thank you.
Professor,
Yes.